Greetings, friends, and welcome to the first class of week 8, where I will be posting the PLC a little bit later, and I'll post the quiz a little bit later. Homework's also due today, so we will get those. We'll get that, and I've got to get these posted out. I forgot to post this, and I forgot to post this, so I will get those going, and you will be able to access them a little bit later, probably in a bit after this video. So hang on for that. Very minimum, it's midnight for these, for the quiz, and since it's got a late start, it might be even a little bit later into Wednesday. So that's going on. I'll get homework 5 started, and we'll get going on some of the homework 5 stuff today, which is going to involve multiple lenses and lens mirror systems, as well as instruments like just magnifying glasses, microscopes, and telescopes. So with that being said, let's get started on this, and we'll go from here. I have here the usual converging lens, and it's now taped up to the board in a show of extreme technology. I have my laser here, and I don't know, okay, you can kind of see that. Let's see if I go this way. If I go like that, so it's going through, and it doesn't look like, where is it? It's hard to see the end part, but there's the end part there. There we go. There's the end part there. And if I move this, I try to hold it there, and I move it down like that, you can kind of see where it goes. Not really super well. That's maybe a little better, but it's getting washed out by the white light here. So it's coming up through about here. Right about there. I think the focal length for this thing is right about there. And if it's not, it's close enough for government work. So it's say right in here somewhere, it looks like the focal length. Just as a basic premise here, what I'd like to start off with is the idea that when we have multiple, I don't want to say objects, when we have multiple lenses or lenses and mirrors in our system, what's happening is we're still treating things as one lens or one mirror by itself, using the object and the image and the focal length, and I should say finding the next image, and then using that image as the object for the next thing that's in line. So the basic idea here behind either two lens systems or lens mirror systems is that we still analyze them exactly the same way as if we had nothing else there. We take them individually. We use a single lens or a single mirror, use the object and the focal length, find the image, use that image as the object for the next thing. So we can still use the mirror or slash thin lens equation in which we then take the image and work it as the object for the next one. So I just say that the image from one of them becomes the object for the next, whatever it is. If it's a mirror making the image or a lens making the image, that image is going to then become the object for the next lens or next mirror in line that we need to analyze. And so we just end up chasing the light and the images from one to the next to the next to the next, and ending up ultimately with a final overall image as a result of looking at the very last thing in line. The thing that we also want to know about is how do we figure out analytically what we expect the magnification and the subsequent height of the final image to be. Well, because of how this works, each lens or mirror magnifies or minifies the object in some way, and the overall magnification is simply the product of the individual magnifications from each stage. So when I find an image here from the first one and it becomes the object for the next one, I can find the the image's magnification and then go to the next one and say, okay, what's the next magnification going to be? And the image that's the product of these two lenses, or lens mirror, or whatever it is the multiplication of the magnification from lens or mirror number one times that from lens or mirror number two. So we multiply magnifications to find the overall. Okay, so we find the overall magnification by doing that, and ultimately that's just the essential process of stepping through a lens and then a mirror, or a lens and then another lens, no matter what the situation. Okay, now we can do a couple of examples ray drawing wise, just to see if we can come up with a ray drawing for example, a lens with a mirror. And so I have my lens here and I have a mirror. Now, hopefully you've been getting to be reasonably familiar with what to expect as you analyze light going through a single object. I mean, not object, but a single element, lens or mirror. So that when you have a converging lens like this and you say, okay, well, where is the object relative to the focal point? You would know that if I said, oh, well, the object is outside the focal point, you'd know immediately a couple of things about the image that should be formed. If the object is outside the focal point of this lens, you should know, number one, it's a real image that's going to be formed. If it's outside the focal length and it's a real image, number two is that image should be inverted. Okay? And number three is it should appear on this side. Normally the way we do things is have the object here and the image comes as a result of the light going through the lens, and the image is formed over here opposite where the object is. Or in other words, where we expect it to be for a transparent lens. Likewise, if I took a converging mirror, I'd be able to say the same things. Object outside the focal length, then I'm going to say real image inverted. And image is going to be where I expect it in positive image distance space. As I move the object inside the focal length, we just switch around and say, oh, okay, now we're inside the focal length, we're expecting an upright, a virtual image, same side as the, if it's a lens, same side as the object, etc., etc. So hopefully you're getting to be relatively familiar with knowing, oh, if it's this, then it's a one of these, right? If I have an object here, then I'm going to expect an image of this type. Therefore, if I take a converging lens and a converging mirror, and I put the converging mirror somewhere over here, I'm not exactly sure where the focal point for this thing is, but we can find that relatively quickly. Let's see here. If I go in parallel, it's coming down through about there, right about there. Oh, there's a lot of spherical aberration in this mirror. I'm going to say it's about here. If I keep that there, I'm going to say that it's about right here. So I'll call this F1, this is F2. I'm just going to put that right there and that right there. All right, so then the question is, what do we get if we shine light through lens number 1? It bounces off the mirror here, and we get a reflection, and then we get the light then making an image due to that, and then a light is then bouncing back off the lens, off the mirror, going back towards the lens, like so. Okay. So I have only a laser beam here, and you are where you are, so there's not going to be too much in the way that I could show you of an actual setup here with an image and a screen. But nonetheless, hopefully we can get to the point where we can imagine this. If I have an object, and I've got a focal point here, it's about there in the middle of my O. So if I have an object outside the focal point here, the question is, where is the image going to be formed from the first lens? So let's assume that I've got the image far enough away, the object far enough away, such that, let's see, where did we say that was? About there? Yeah, about here. So let's have the object be far outside the focal point. We'll start with it, say, over here. Okay, and so what we'll do is we'll start by tracing this and looking at the ray diagram for the first one. I'm going to go ahead and remove these from the wall here. That one's already traced in, so I can draw this. Alright, so that right there is the mirror. And my lens should be about here. Okay, and we're assuming a thin enough lens such that, again, all the refraction happens at a point in the middle of the lens. So just sketching this out, what we do is we have the incoming ray parallel with the axis, like so. And going down through the focal point, about like so. Missed a little bit there. I can utilize this focal point here and find one that goes like this, which then comes out here. Okay, and now we're taking a look and seeing, okay, I've got an image that looks like it's going to be formed right about here. So I'll call this image 1, as that's the first image formed from the lens. And notice I haven't used the mirror whatsoever. But what I'm going to do now is say that image there is the object for the mirror. And so now I'm going to trace the rays into the mirror and out. And I know I've got an object which is outside the focal point of the mirror. And therefore I know what kind of image I should be expecting. All these rays should bounce off, come back, and refocus over here with a new image, a new real image. And that real image should be inverted. Okay, so let's take a look at what that means. If this comes in parallel, I'm just going to use the exact same ray that came out parallel with the axis to make this image. And I'm just going to continue it through here. And it's going to bounce off and go through the focal point, which I want to be a little bit more like there. It's going to bounce off and come up through the focal point like about there. Okay, I'll start labeling some of these rays because it's going to start getting kind of crowded in here soon. Okay, this one's coming in, that one's going that way, this one's coming back. Okay, and now part of the thinking that I'd like for you to get used to is that even though I've only drawn the two rays from the object through the lens to the image, remember this is emitting all sorts of rays which we aren't drawing, which are going through the lens and helping to form this image. And therefore, when I think of this image, since it is real, light is actually coming away from there in all directions. So I should be able to treat this as if it's a source of light, which it kind of is, and it's emitting light rays in essentially all forward directions. Not so much this way, because the light is essentially trying to go left to right here, but in the forward directions it should be emitting, I'll have more than 2 rays to choose from, let me put it that way. It was a happy coincidence that this one came in and I could join right up with the one that I wanted to use for the mirror, but now I'm going to have to use another one for the mirror, and I will go ahead and use the one that's going to be going up from there and through the focal point, which is right here, like this. That's going in, and now it is coming out, and it's going to be going parallel with the axis, so it should be going something like this, like that. And it looks like my second image is apparently right about here. Okay, so image number 1 is there. Image number 2 is here. Okay. Now, for these 2 images, I guess I have been a bit remiss here. Let's take a look at the answers for the 4 questions. For image number 1, which is right there, I have a object to the left, light coming through left to right, through a converging lens, making a real image. We know that's a real image. It's a real image that's opposite the side of the lens from the object. It is inverted, and by my eye, that looks to be minified. Now I'm going to take this as the object. I'm going to go here to the lens, and I'm going to answer the 4 questions about image number 2, which is here. Image number 2 is also real. Light is actually converging to that point. This is also inverted. Notice that this image, which was produced by the lens, is inverted compared to the original object, which is upright. This is inverted. Now the image is back to being same orientation as the object, but it's inverted from this one. So the question is, do we think of it as inverted, or do we think of it as upright? Where are we now? Doesn't really matter super much, because we're still in the intermediate stages here. We still need the final image of the light bouncing off the mirror and going back through the lens. This is an inverted image compared to that. It is also apparently seeming to be minified, lower than its height here. I started with an object that was 1 box high on my board. This is about a half a box high. This is about a third. It's definitely lower than that. So we would say it is definitely minified and inverted right there. This one is here, like that. If I darken them in, hopefully that helps see a little bit better. I'm now going to take these 2 rays. Well, I don't know if I'll use the second one, but I'll take at least the one that's coming out parallel as my ray to enter the mirror, such that I can hopefully find the final image, because I am over here. Here's my eye, I'm looking over here at light coming this way back from the mirror. So I have to go through the lens the first time, off the mirror, and through the lens the second time, and that will be my final image. So even though we have only a 2-component system here, there are 3 images to deal with. I'm going to go ahead and take this one as being parallel in to the lens to there, and then going down through the focal point, like so. Okay, that one is coming this way, and going this way, and going that way. And I'm going to treat this image as an object for the lens again, assuming that light is essentially getting emitted from this in all the forward directions. And so what I can do is go down through this focal point here and hit the lens about there. And it's going to come out parallel. This is going that way. And it's going to come out parallel about there. Looks like the image is formed about here. Image 3. Okay, image 3 is once again a real image. It is once again inverted from its object, which is image number 2 over here. Okay, and ultimately could be minified a little. No, maybe it looks like it's about the same size. It looks like it's about the same size as image number 2. Maybe a touch smaller. Hard to say. Hard to say. But nonetheless, I have ultimately here formed 3 real images, all of which were minified and inverted from the previous one. Now, if I want to describe the final image, because what we've been doing is we're out here, we have an object, there's light going in, we're looking at the lens at light coming out. If that's all we're doing, we really have no way of seeing these images here. All we see is this image here if we're out here. Therefore, what might be useful is to think about the 4 questions for image 3 relative to the object. The object is pointed up and my image is pointed downwards, so this is definitely an inverted image. It is also definitely real, as these light rays have converged to this point. It's on the same side as the object, so that's a little weird. But nonetheless, from its previous object, we would have said it was a positive image. So, and what's the last thing? It's definitely minified. It's inverted, minified, and real. And at least those 3 questions can make sense to have answers to. The answer to the question about where the image is more simply to help us understand how it's related to the object and the lens. So as these are real images, and we've gone from a lens in which we'd expect a real image to be on the opposite side of the object, to a mirror in which it should be on the same side as the object, back to a lens in which it should be opposite the object again, and now we look here and say, well, it's on the same side. So the question of where the image is kind of losing its meaning. The answer to that question is kind of losing its meaning as you start going through this process. The other 3 questions, though, still very important. Real, inverted, minified, or should I say, if it's a real or virtual, magnified, minified, inverted, upright. The answers to those 3 questions is still quite meaningful here. The one in which it's locating the image is simply giving us an idea of what the sign of the image distance is. And ultimately, I don't think necessarily we care if our eye is just out here and we're trying to find an image. Okay, the analysis of this would then be exactly as we kind of described as we went along and did each image. Therefore, you could suppose that had I started with an object here, which is well outside the focal length of that first lens, and so we could possibly say, well, this is, for example, if I wanted to make up a few numbers here, this is a 20 centimeter lens. Maybe this is about a 15 centimeter mirror, or maybe a 10 centimeter mirror, and the object is what? Oh, it's definitely double the focal length out of there, so maybe it's 60 centimeters away to some start with like that. If we wanted to chase through some numbers really quickly, we could do that. Let's go ahead and suppose that the focal length 1, which is for the lens, is 20 centimeters. Focal length 2 for the mirror is 10 centimeters. Both are positive, so I'll needlessly put in the plus signs near them. And I'm going to start with an object distance of 60 centimeters. 3 times the focal length. That's not so bad. Question is, what is the quality of the final image? So let's go through and see if we can find out about where it is and about what its magnification looks like. And we just chase through the image as we have done with the ray diagram. So, if I start over here, I'm going to say my first image. So for image 1, I would get 1 over Q1 being 1 over F, F1, and 1 over P. So this is going to be 1 over 20 minus 1 over 60. and that looks like 360s, and that's 260s, which is 30. So Q1 turns out to be 30 centimeters. Q1 is therefore 30 centimeters, and here's where you just have to kind of pay attention a little bit. Q1 is 30 centimeters from the lens. Where is it? Here. Okay, that's the first object distance. Now I'm going to ask that, I'm sorry, that's my first image distance. Now I'm going to ask, where is this image relative to the mirror? So I have to shift now, right? And I have to know how far away is the lens from the mirror. Okay, that looks like it might be, gosh, that might be about a 60 centimeter distance. If I call this something like distance L, let's suppose that L is 60 centimeters also. Okay, therefore, if L is 60 centimeters, to find image 2, I'm going to do the same exact equation here, which is not showing up quite as well with the green. Let me try this. Image 2. Okay, that looks like it might work. Now, if I got 1 over Q2, I'm going to have the focal, which is 10 centimeters for the mirror, and the distance away, well, that means this image slash object has landed about halfway between these two, and so this is going to be 1 over 30. That's going to be 3 30s, and so this is 2 30s, and therefore Q2 is 15. And that's 15 centimeters from this mirror over here, which means the focal point was here, and my image from the mirror is right there. Okay, that's the focal point here. That's the image there. Okay. And if I go 15 from the mirror, but I know there's 60 apart, that means it's 45 back to the lens. That means I'm going to go to image 3, and I'm going to say 1 over Q3 is now back to the 20 centimeter lens. I'm going to have 1 over 45, darn. And I'm going to have 2.5 minus 1, so about 1.5 over 45, 1.5 over 45, which is 45 divided by 3 halves, which is multiplied by 2 thirds. So, oh, we're back to 30 again. Okay, good, 30 centimeters. So we're back to 30 centimeters. That is this right here, which actually looks like it's landing about halfway between my lens and object. So that's good. Okay, so that's where the image is. Let's take a quick look at its magnification. Its magnification here in the first section, we should be able to calculate M1 as being negative Q over P, 1 and 1. Let's see here, I've got a Q1 of 30 and an object distance of 60. So yes, in fact, this is negative a half for the first one. Here for M2, again, negative Q over P, Q2 over P2, and P2 is 30. Q2 is 15, so this becomes 15 over 30. Yep, again, it's a half. And for 3, it's 30 centimeters. No, the object is 45 and 30, so this turns out to be negative 30 over 45. Which is 2 thirds, negative 0.67, say. All right, now I'm going to multiply 1, 2, and 3 in order to find the ultimate overall magnification of this, so I guess it's really quite a bit tinier than it seems. Where it's a quarter from this, and then it's 2 thirds of a quarter, which means it's about a sixth of what it was. near enough. Notice the sign though. I'm going to multiply a negative, and a negative, so it'll come out negative. About a negative 0.15 or 16 or so. All right. So that's dealing with where the image is and how to find the magnifications. Not to mention the ray diagrams, which again, super important to try and figure out how to conceive of the image that you're expecting. Okay. All right. Good stuff. Now, you can certainly modify this greatly, and I think this is probably the only example I'll do of this type of thing, but you can certainly imagine that I could scoot this object way in here. In fact, I could put it inside the focal point. If I put it inside the focal point of the lens, what do we expect happening? I'm going to get a virtual image that should be back over here. Now I've got a virtual image over here, which is going to make an image off this mirror here, and it's pretty far away, so it's going to bounce off and be kind of small in here. So I'm going to get a large magnification from the virtual image, a small magnification from the mirror, and now this thing's probably going to end up somewhere in here, halfway, center point's 30, so this is in between. We might get a touch of magnification out of the lens, but notice what's going to happen. I'm going to have an upright image from the virtual. It's going to flip over to become this real image here, which is then going to flip over again, and I should end up with an upright final image. So there are many different permutations to this. I encourage you to take a quick exploration and see if you can follow the ray diagrams for them, just so that you have those in your memory banks. And don't forget that you can work through the thin lens / mirror equation at every step as if the image from one was the object for the next. I will say one other piece about this, and that is, no, I will say two other pieces about this, and that is, one is I can change this lens, make it a diverging lens, converging lens, whatever. I could change this mirror, converging mirror, diverging mirror, plane mirror. Either way, we treat it exactly the same. All right, we go image from this, object for the next. Object forms an image here, that image is object for the next, and we just chase them through. That's the first thing I'm going to say. The second thing I'm going to say is that while I took the object here and scooted it inside the focal point and it made a nice virtual image, well, what would happen if I took the object and I was really close to the focal point but still outside it? I should still get all the same image qualities that I would get when I had the object over here, but there's going to be one difference. If I'm scooting the object closer and closer and closer to the focal point, what's happening to this image number one relative to the mirror? Well, as the object gets closer, closer, closer to the focal point of the lens, then the image should be going further, 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 further. I can make the image number one be so far from the lens that it's already past the mirror. This may cause you some consternation. However, I suggest that it does not. And I suggest that we stick with our sign convention. And we think carefully for a minute and say, okay, if I make an image from this lens such that it's past the mirror, yet I would like to use that image as the object for the mirror, how do I do that? Well, the object is not where we expected it to be. So let's consider the algebraic sign of the object distance now. To this point, we have not considered anything other than positive object distance, because the object was over here and light was coming this way into either a lens or a mirror. Well, what happens now when I have an object over here that can't be actually casting light, right? But for our purposes and the modeling of the stepping through of the images and the subsequent objects, this is simply a negative object distance. So that when I go in and plug it into the mirror equation, in this case the mirror, I am going to have a negative object distance, which would have meant, for example, here, that would have been, for example, a negative number right there, which would have flipped this sign to becoming positive. And what would have happened would have been that I would have gotten, in this case, let's just chase this through and suppose it was a negative 30, so this becomes a positive plus. Now I get 3 over 30, 4 over 30, I still get a positive image distance. It's still positive, okay? What does that mean? It means the image is still where we expect it on the other side of the mirror, okay? Like so. So it's over here. We're keeping image distance positive over here for this mirror, and object distance is negative over here for the mirror, okay? All right. So keep that in mind. The object here in this case would be known as a virtual object, and it would have a negative object distance. Okay. With that being said, I'd like to go on and talk about the simple magnifying glass and what it means to look at something. Because to this point in the class, what we've done is we have considered the magnification of an object, the magnification of the image if we were to put a screen and catch the image there, okay? However, our eyes do not function this way. When we look at things, we are actually introducing another component to a lens and a mirror system, because our lens of the eye focuses the light and makes an image on the retina in the back of our eyes. Then we have to consider that as another thing in the kind of the sequence of events here, okay? So let's take a look here. And let's think about what the magnifications mean. Because we are going to have slightly different definitions of magnifications when it comes to multiple lens systems. All right? And that is because we've introduced the eye. If we're looking at the image and we're forming the image of that image on our retina, then things are a little bit different. So let's begin with the simple magnifier. And I'll try and show you what I mean by the magnification changing. Okay, the simple magnifier is the magnifying glass. All right, now the magnifying glass, you may have never used one, which is kind of an interesting proposition for me. But if you've ever tried to focus the sun's rays in order to start a fire, hopefully a campfire, and hopefully it's in a well-protected and appropriately zoned area in which campfires are allowed and in fact encouraged, rather than just starting some stuff out in the middle of wherever. We don't do that type of thing in California, do we? No, we don't. Suppose you're taking the sun's rays and you're attempting to focus them, right? Then you're using a converging lens, because the sun is, for most practical purposes, infinitely far away, and therefore its rays will converge at the focal point of a converging lens, because those rays from that sun will be paralleling coming on your lens. If you want to consider taking an object in your field of vision, but magnifying it so perhaps it's easier to read, okay? You'd say, well, that's a very easy proposition. Suppose I have my pen out here at this distance and I was going to draw how much my field of vision, how much angle in my field of vision does the pen take up? Well, I'd be able to draw my eye here, and I'd draw the pen over here, and I'd say, well, if I have a pen, I'm holding it about arm's length, so it's probably about here. I have a pen right about here, like this. Then you'd say, well, all I need to really do, if I'm concerned about how much of my field of vision is this pen taking up, all I really have to do is think about the rays of light which are coming into my eye from the extremes of the pen. That means from here and here, like so. Those light rays, which are going this way, incidentally, are going into my eye. And you'd say, well, wait a minute, are those rays making an image on your pupil? Well, no, they're not, because they're not coming from the same place on the pen, okay? But what they are doing is they're then going into my eye, focusing, and then coming out like this is a pinhole camera, okay? And so I'm getting a really tiny, here's my retina back over here, and that one's going there, and that one's going there. And so I get an image of the pen that's right here, okay? That's maybe a little bit large for a retina, but that's okay. So I'm getting an image of the pen. Yes, it's upside down, and you probably know that your brain flips it over for you so that we don't think that we're walking on ceilings and looking up at floors and things like that. Nonetheless, the angle that this object takes up in my field of vision is, right, simply the angle between those two rays. Now you'd say, well, I'd like a simple magnifier. Okay, no problem. Here's your simple magnifier. Look at that. Now it's way closer. I can see it. It's bigger. It's a lot bigger than it was because over there it took up only a little bit of my field of vision, and now it's taking up a lot more of my field of vision, so I've just magnified the pen. This is even less than the simple magnifier, okay? So now suppose I take the pen, it's the exact same height, all I have to do is move it to say here, and I'm going to say, all right, here it is again, and I have a little thing right here, it's about the same size, maybe it's a bit thicker that I've drawn it over here, so let's just thin it out a little bit, it's about like that, okay? So it's the same size, but now if I think about the rays from the top and the rays from the bottom, can you see they're going to be making a wider angle in my field of vision than they were before, such that this, if I can just freehand from there to there, this angle is a new theta, right? If I call this angle the one that was this one to this one, maybe I'll call that theta naught or something like that. So that the magnifying effect is essentially this angle divided by that angle. It's how much I've magnified it relative to what it was, right? This is how much bigger it is just by doing this. Now, we can have lenses do the same things for us, specifically the converging lens. I should mention one other thing about this before I move on. There is a point of no return. Well, there's a point of marginal returns, okay? In other words, I'm going to take my glasses off, I'm going to move this pen, and at some point, I can't focus on it anymore, right? I'm going to start squinting on it. If I try to keep my eyes relaxed, and I'm going to try reading the writing that's on the side of the pen, but I'm going to keep my eyes relaxed. Okay, about here it's starting to get blurry. Yeah, so I'd say maybe about there is my final, I would say that's about my final point at which I have to squint past this. If I pull the pen past this point, I have to squint. So let's just see about how far away this is. I'm going to do it again. Yeah, about there. So I'm looking at about 40 centimeters. This is called the near point of your eye, okay? This is the near point of your eye. I can certainly bring it in here. I do have to squint a bit more, and by this point I can't squint enough. So you'd say maybe about there is my final, that's about my final approach right there. That's the closest that I could possibly get it. And that's about 25-ish centimeters or so. And that's a typical near point, okay? So you can try this at home by just measuring your near point. Try to relax your eye though, and then try to focus and squint on it and see how it goes. Alrighty, so basically, the point of a simple magnifying glass is to do this for us. okay, is to do exactly this. You can imagine that a lens would do this for us, yeah? Because what I would need to do is put here a converging lens, right? I'd put a big converging lens right about there. And what I'm going to do is make the focal point of that lens kind of near where this object is. Now remember, the focal length has to be further away than the object is, otherwise I can't make an image like this. But imagine if I went to drawing a virtual image for a converging lens, it would have looked like this, because I would have said, well, here's my axis. Okay, I'm going to set a focal point. I'm going to have to be a little bit smaller than this diagram here. Well, no, I don't. I can go out here. I got a lot of room here. Okay, so here's my object, right? Here's my candle. I'm going to change the pen into a candle. And I'm going to say, okay, where's my focal point? All right, the focal point is going to be over here. There's F. I don't need a 1 here. There's F. It's quite a ways away. Okay, so it would be about over here. And I can think about what the rays are going to do. Okay, I'm going to go in here parallel. And I'm going to go in here, let's say through the middle. I'm going to take the middle one just because that's an easier one. Like so. Okay, now I'm going to take a look at where do these ones go. Looks like maybe about here. Whoops, that kind of got a little off track there. You have to keep on going. Keep on trucking. About like that. Whereas this one is going to come out of the lens, go through the focal point here. Of course, right as I do that, it moves. Okay, so there you go. These are my 2 outgoing rays right here. Let's see if you can even see those. Yeah, you can see those. Okay, those are my 2 outgoing rays. So if I have my eye somewhere over there, this is rather large for a diagram, but nonetheless, if I have my eye somewhere over here, then what I'm doing is I'm looking at the image formed, which is virtual, right? Because these things, these rays here are so close to parallel that I'm going to have to trace these back. I'm going to get an image that's way up here. Let's see, the edge of the board that you can see is there, so I'm just going to put the image about up here somewhere. Let's say, and it's going to be going, it's going to be following that line right there. So it's going to be about this big. Okay, and even that I had to kind of push the line up a little bit in order for it to see. That's supposed to be exactly parallel with this line right here that's going up, but you can see I've increased the angle a bit there. So that's a large image, and in our eye, okay, it makes, maybe, actually, I think I do need to cut this down a little bit. It is supposed to be along with this one, so let me do that again. It's coming like this. Maybe about there. Maybe that's a little better of an angle. Okay, we're going to do that again. It's about here. Okay, so think about this angle that is made in our field of vision now. It's this angle here. That's theta. That's the angle of the magnified image in our eye, right? Because if we're looking at this, we're looking at these rays, for example, this one right here, which goes right through the center of the lens, ticks the top of the object and makes ultimately the image back there. Okay? Now suppose that I think about, if my eye is, say, right here around the focal point, now think about, for example, how big is the object originally going to be in my eye if my eye is at the focal point? Okay, so let's take a look at that angle. Maybe I can darken this in enough with the red so that we can see that. I'm going to have a pretty long ruler here. Okay, so if you can quite, if you can quite see that line, there's an angle here, right there. That's the angle I'm interested in, right there. That's the line that my eye would see at the top of the candle, such that the amount of angle that is taken up in my field of vision is this angle here, which I'm going to call theta naught. All right, and I think you can see, if you're just comparing this angle to this angle over here, I think you can see we have definitely magnified it. And therefore the magnification of this simple magnifier is basically the angle that we magnified divided by the angle that it wasn't magnified if we just were looking at it. Theta over theta naught. Okay. Okay. So that's basically a magnifier. Now, the reason we use angles is because our lateral magnification kind of fails us a little bit. And when I say lateral magnification, I mean the magnification that we're used to, which is negative Q over P. Why does it fail us? Here's why. Because a relaxed eye, if you're not squinting and you're not trying to see something, if you're just looking, you can see objects that are infinitely far away. And there was a famous exchange between a manager in Major League Baseball and an umpire. And the manager said, "You can't see anything." And the umpire goes, "Well, I can see the sun and it's pretty far away." So the sun, and he's right, the sun is essentially infinitely far away. And in our field of vision, the moon takes up exactly the same amount of angle. Now we know the moon and the sun are not the same size, but they take up the same angle in our field of vision. Therefore, we'd say that the magnification from one to the next would be 1, right? But in this case, we've managed to magnify this image above what it would be if we were just looking at it. The reason we do this, as I was saying, the lateral magnification fails us because if we have a relaxed eye, we can take that image, the one that's formed by the lens, and put it at infinity. In other words, what happens when this object is sitting directly on top of the focal point? We know that makes parallel outgoing rays, and therefore we would say there's no image formed. But, and there isn't, by the way, that you could catch on a screen, but in our eye, there is, because that's just parallel incoming rays, right? If that object was sitting on the focal point, and these were parallel outgoing rays, and I was looking at them, they would enter my eye, focus, and I'd be saying, "Oh, there's an image over there." I'd be able to see it. So we can focus parallel incoming rays due to an image that is produced infinitely far away. If it's infinitely far away, it had better be infinitely large, because otherwise we definitely can't see it. Okay? So that's why when we start thinking about, well, how come we're going to this other definition of magnification? It's because we're dealing with infinity over infinity, or infinity over focal lengths and things like this. So once you start realizing I can't catch this on a screen, but a screen doesn't have the focusing properties of our eyes, so this is actually a more useful definition of what the magnification of something is when we are looking at it. Right? If it's a screen, we can use the lateral magnification the way we have been using. This is known as the angular magnification, and ultimately is far more useful when dealing with quantities that we look at and can see in our eyes. With that being said, I can sketch out the microscope and the telescope for you because ultimately it depends on having a simple magnifier. Both instruments depend on having a simple magnifier. So let's take a look at, let's see here. I think I wanted to say one other thing about the simple magnifier. Yes, I do. If I hold on, don't erase anything. Okay, great. If I look quickly at making an expression for the thetas, remembering that we're in a small angle approximation here, theta naught is basically like the tangent. So in a small angle approximation, I don't know if you're aware of this, but in radians, the sine and the tangent are approximately the same. And they are approximately equal to the angle itself in radians. So if I take a look at the height of this candle and I call it h, then it's about the focal length of this lens away. So theta naught, I could really write as height of the object divided by the focal length of the lens. If I think about writing something similar for the theta here, right? Then for the theta here, what I'm going to think about is, theta naught, I did that wrongly. Theta naught, wait, I did this wrong. I want theta, which one's theta? It's that one, right? Okay, it's this one over here. So the theta that I'm thinking of should be, that's the one that's h over f. Yep, that's wrong. Okay, this is theta, which is h over f. Sorry. Okay, let's take this out of here. I got to make that something else. This is theta naught. And theta, this one is the height divided by, because I looked at the wrong thing here. This is theta right here, this angle. Right there, that's theta. Theta naught is this one right in here. Okay, I got that backwards. So this is h over f here. And theta naught is if we're holding the object close enough to our eyes to where we can see it, then we would say it's at our near point, right? So this angle here is essentially the height of the object divided by the distance away the object is from our eye, and that should basically be our near point distance, which I'll just call our NP. So that if we thought about fooling around with the magnification, what it's going to approximately be is the h's will go away, and I'll get the near point distance, which flips up to the top, divided by the focal length of the lens. So for a simple magnifier, it depends on how close your near point is and what focal length lenses you want to use. All right. Okay. Yeah, hopefully that makes sense, because the theta naught is the situation without the lens. It's as if you're just holding the object here in front of you and it's taking up theta naught in your vision, okay? And now I put a lens in front of it, and now all of a sudden I'm getting that image, and that image depends on the focal length of the lens. Whereas in the theta naught condition, I didn't have the lens here, I was just holding it and trying to see it. And now I'm comparing how much in my field of vision does this thing take up versus the image, which is much larger. All right, so it should be about something like that. Now, if I take a look at the microscope or the telescope, they're basically the same thing. What's happening is, if you're using two converging lenses, you're taking an image of something and you're projecting it at or near the focal point of the first lens. And then you're taking another lens and you're trying to use it as a magnifier so that you take the image formed by the first lens and you're trying to use this simple magnifier effect. Excuse me. Okay. So let's take a quick look at the compound, or not the compound, just the microscope, a simple microscope. And if you have a reflecting telescope, for example, you'd be able to see this, because there should be a converging mirror. Light comes to the focal point, and then what you do is you basically try to magnify that image with a simple magnifier. All right, so if we take the microscope, what's going to happen here is we're going to have an object here which is relatively close to the focal point of this lens. So let's say it's about there. Focal point is there. So we'll call this f1. And what's going to happen is I can draw my rays from the object through this first lens, which is usually called the objective. And I'm going to sketch these out this time around. So I'm going to go in this way and down that way. And then I'm going to go straight through the middle like that. I'm just going to confirm with my third one here, which is going down like this and out like that. Okay, that's not bad. Wow. All right, so my object from the first lens forms an image here, which is quite large and inverted. Which is kind of what we'd expect, because the object is really close to the focal point. So we're getting a little bit of magnification already. Now I'm going to take another lens and I'm going to look at that image and try to magnify it. So that means I'm going to take another lens over here whose focal point is basically right here. Focal point for lens 2 is basically about right there. And so what's going to happen is we're going to get an incoming, which is going this way. We're going to get one straight through, and you can see these rays are going to be approximately parallel, which is good because I'll get them into my eye, and they will make an image which is large, which is very large and inverted. Whoops, a little more like that. Which is large and inverted, because what we're doing is we're making a virtual image of this real image. Okay, by scooting this lens close enough such that its focal point falls right where the image is from the first lens, I can now make a large virtual image which magnifies it greatly. And since that's going to be an infinity away and infinity large, we have to go with angular magnification for the second image. Okay, so the overall image of the microscope is the multiplication of image number 1's magnification, which we could approximate. This is negative q over p, and the focal distance and the object are about the same. So p is actually approximately f, and that would be f1. Whereas the image here is, well, I've drawn it a little weirdly, but very often the focal length of this one won't be quite as large as I'm making it here. It'll be a little bit smaller. It would be almost the distance between the lenses. Okay, I called the mirror lens distance in the last example L, so I'll call this L from here all the way over to there. I've drawn this poorly, so it looks like this is not a good approximation, but typically this is an okay approximation because we have a distance between the lenses in the tube of the microscope. So this is usually approximately distance L for the lateral magnification of the first image. And then the second image we would get by doing this, and that would be f2 here, because that's the situation in which I'm magnifying it to make an infinite image. And as soon as we start magnifying to make an infinite image, then you know you've got to go to angular to analytically see it. Otherwise you're dealing with infinities and stuff like that. All right, so that's the basics of how a microscope works. It's a fairly simple application of the magnifying glass, right? And that's all we're really trying to do, is make an image such that we can look at it with a magnifying glass and have it be big and large in our field of vision. All right, and the telescope essentially works the same way. You take, you notice I have a short focal length here and a longer focal length here. You kind of flip those around and you'll get a telescope. Same basic idea will hold. So, looks like we've come to just about the end for today. So I will bid you happy rest of your day, and we will be getting homework 5 up. Like I said before, I haven't quite got the PLC or quiz up for today, but hopefully I will be able to do that soon, and we'll go from there. So happy rest of your day, folks, and I hope you enjoy some lenses. If you don't wear glasses, then you don't get to see the world in a virtual or virtual or converging way. But nonetheless, be well, and I will see you next time.